Alright, good afternoon / welcome back. That's a little freaky. There we go. All right. Short class on Monday, and I had to go to a tenure reception. So I got tenure in last spring, and normally they have a reception a few weeks later. Well, I got tenure about 14 hours before everything started locking down. So this was delayed a few times and then happened through Zoom on Monday. Thank you. Appreciate it. Yeah, so that was just a informal get together and say a few words kind of thing, which I was going to skip, but I was told that it was probably a good idea not to skip it. So I left you a video recommendation to watch. So hopefully people watch that, and we'll talk about it today. But any questions up front on that video material? An FSM is a finite state machine. So as in engineering 250. Let's see, what interprets the BNF definitions? So BNF is largely, a way to describe in human readable form the syntax of a language. It's not necessarily intended to be interpreted by a machine. It's more of a higher level thing. But let me see what I've got here. Yeah, so I think this was in the video, right? This is BNF. So FSM is a finite state machine. Same thing we talk about in 250. So what is a state machine, first of all? So yeah, let's talk about this. So, most of you have had Engineering 250. It might have been a while ago. A few people are taking the course before 250. So what is a state machine? A state machine is, a system that has a memory, basically. So state basically refers to the condition of the system at this moment, which means its behavior depends not just on the inputs, but on, the current setup of some pieces of the system right now. So, combinational logic that we describe with a truth table, you put in a set of inputs, you get a set of outputs. You come back in 100 years, you put in the same inputs, you're going to get out the same outputs. The behavior is completely a function of what you're putting into the system. And it doesn't matter what kind of crazy stuff you've put in the past. It doesn't matter if 1,000 monkeys came in and flipped all the switches 1,000 times. Right now, if I come in and I put in a set pattern of inputs, I know exactly what the outputs are going to be. Okay, that's a combinational circuit, and we use a truth table to describe it. A state machine depends not just on the inputs, but on its current condition. And so if 1,000 monkeys come in and flip 1,000 switches 1,000 times, now I come in and I put in my set of inputs and I expect it to give me the sum. It might do something different, like read me a work of Shakespeare or something. So it basically has a memory. And most, machines that we deal with are state machines. So your laptop is a perfect example of a state machine. When you hit the enter key, who knows what's going to happen, right? It depends on what the current state of your laptop is. If it's at a place where it's waiting for you to, hit the enter key to type a bash command, then it will run a bash command depending on what keys you hit beforehand. If you hit PWD, it will show you your current directory. If you did rm-rf star, it will delete all your files. So simply knowing I'm hitting the enter key, what's going to happen, well, that's not enough information. You've got to know the current state. And if you clicked on a window where you had typed an address into a URL box on a browser and you hit enter, well, now something very different is going to happen. Okay, so state machines are kind of the more interesting version of digital logic. Could you have an analog state machine? We always talk about digital circuits. 250 is a digital logic course, and we learn state machines in there. Could you have an analog state machine? What kinds of things might that look like, if it's even possible? Maybe with switches, maybe with like knobs and dials. Yeah, dials are good. And meters that like...
Maybe gear shifting in a car?
Oh, maybe gear shifting in a car, sure. What happens when you push on the stick shift? Well, it depends on the stage. If you happen to have your foot on the clutch, then one thing will happen. If you don't have your foot on the clutch, something different will happen. So yeah, this is a general concept. And yeah, so it would work on ranges, right? Perhaps. So here's a question: is the universe a state machine? I'm gonna light some incense for that one. I'll go with mood lighting even. There are senses in which we might, reasonably think of the universe as a state machine. Although this gets into, other areas like, is the universe deterministic? And that's a philosophical, theological, and physical question. But even if it's not deterministic, even if there is something like, free will or randomness in the universe, could it still be described as a state machine? And we'll come back to this at the end of the course today. Yeah, so this is going deep down the bunny hole. But we'll close out today talking about non-deterministic Turing machines, which are like Turing machines but with a genie inside, and we get into some really interesting stuff. If a sun goes nova and no one is around to witness it, does anybody care? Those are good questions. And that's not a silly question. The tree falling in the forest. That's actually the cornerstone of one of my cell matrix lectures, about the sound of one hand clapping and the sound that a tree makes. But anyway, so state machines, right? Systems with memory. And then a finite state machine has a finite number of states, and most systems we're going to talk about have a finite number of states. You wouldn't want to build a circuit in Engineering 250 where the schematic required an infinite number of 7404s and an infinite number of wires, right? Because you'd still be building it, and it would be 10 points a day deduction for being late. So yeah. Finite state machines are the ones we mostly deal with. So BNF is a way to describe language, right? But it actually describes a state machine also, and there's correlations between these, which we'll dig into a bit also. So this is BNF for C, and the bulk of it is pretty simple. There's a lot of of nuanced detail down here, but you know, what's an assignment operator? It's any of these things, right? It's an equal sign, or you know, any of the things that do something and then assign. So like plus equals, and so on. What's a unary operator, right? Plus, minus, tilde, and so on. These are things that can be applied to, you know, a single argument. And most of this is, you know, it doesn't feel like there's a whole lot in here. A jump statement is either go to followed by, you know, a label, or the word continue, or the word break, or the word return, optionally followed by an expression. And if you follow this, right, you can take a set of characters, a set of text, and say, you know, does this represent valid syntax? So if you have something equal sign something else, you can say, is this an assignment statement? Right? Well, what's an assignment expression? It's a conditional expression or a unary expression, etc., etc. These things are tricky to write, but the process of writing them can help you understand more about the syntax that you're dealing with. And I do have a little bit of code in here. This is the BNF for an arithmetic expression, right? A simplified expression. It's a left expression followed by an operator followed by an expression, or it's a left expression, or it's a minus sign followed by an expression. And the left expression is, you know, a variable, a number, or a parenthesized expression. For operators, a variable is an alpha followed by a variable, or just an alpha, and a number is just a bunch of digits. So this is just a comment, right, in a C program, but what I did was I actually wrote some state machine description corresponding to this BNF. So this is something that's supposed to parse an input string. And basically, what I'm doing is I'm looking to see if I have an expression. So this stran is saying, do I have an expression, an exp? And if I do, then I'm going to go to state 1, which says, am I at the end of my input? And if I am, I'm going to say success. This was an expression followed by the end of my input. Okay, what is an expression? Well, if I find a minus sign, I'm going to switch to state S4, and state S4 is going to look for an expression. And if it finds one, I'm going to say success. So this set of code is saying if I have a minus sign followed by an expression, I've got an expression. If I didn't find a minus sign, I'm going to see if I have an L expression. And if I do, I'll switch to state S5. S5 will say, do I have an op? And if I do, I'll switch to S6, and S6 says, do I have an expression? And if I do, I'll say success. And this picks up an expression, could be a left expression, an op, and an expression. And if I found that I had an expression, and I switched to S5, then, you know, I was looking for an op. But if I find an empty string, right, if I just found a left expression, I'm going to say success, and that picks up this idea that an expression could just be a left expression. So this is a description of a state machine, right? And it's written in C with a bunch of macros that I created, but it's basically coding up a state machine corresponding to this BNF. And it just kind of goes on from there, right? So what's a left expression? Well, it could be a parentheses followed by an expression followed by a right paren. Or it could be a variable, or it could be a number. So you build up this whole state machine description, and then to parse a string of input, you basically just call parse. And if it returns true, then you know that your input matched whatever your BNF was supposed to identify. And if it doesn't, well, as it's parsing through, I keep track of how deep you get into the string before you're hamstrung and you can't go any further. And so I'll just print out a little arrow that far in from the beginning of the string and say, hey, there might be an error around here. I'm going to ignore all of my warnings. So I don't remember what an expression is supposed to be. 2 plus 3, that's fine. 2 plus times 3, there's a problem right there. Apple plus b minus xx. Right, that works fine. Apple plus b minus. Right, you do that, and it finds there's a problem here, saying that there's something wrong with that. No, it's not Ignore Warning Tuesday, but we're not in a C programming class. We're in a discrete structures class, so it's actually Warning Wednesday that we get to ignore warnings. Sorry, I thought that was clear. All right. So yeah, so I mean, this is basically taking that BNF and generating code that lets you parse something. Right, and we'll tell you if you've got a good parse. Or if you've got a problem. And there's lots of stuff that does this. There's things like Yak and Lex. Yak is yet another compiler, YACC. And it's something that you can feed a description of a language into, and it will create a compiler for you that will, process the syntax of this. This is just one version. This was a package that I found when I was an undergrad. It was actually part of the runtime library for VMS, an old operating system on the VAX. And it had a package of this, and so when I switched over to doing everything in C, I missed having this capability, so I wrote my own macro package for this. And it's just, it's just all this horrifying stuff. 1985, there you go. So 35 years ago. But it's a bunch of macro definitions. So a init_state is a macro, and n_state, and here's my transition, and here's my sub-transition, and here's some terminal symbols, and so on and so forth. And I hope I never have to go in and actually figure out what any of that stuff does. But anyway, so yeah, so BNF is potentially useful stuff. All right, and then state machines for language recognition. So you saw some examples of following a state machine and getting to a known state means that you recognize the input pattern. Any questions so far on the homework? Yeah, let's try number 3. Sketch a state transition diagram for a machine that recognizes the string 1 1 followed by a pattern of 1 0. So let me do a different one just so we don't take away all the fun. So let's match the pattern 1 0 1 followed by a succession of 0 1 to the n, where n is greater than or equal to 1. All right. So I'm writing it in this notation. This means, a repetition of this pattern n times. And since n is bigger than or equal to 1, I have to have this pattern at least once. So what strings should our system recognize? 1 0 1 always has to be in the beginning, followed by 0 1. 1 0 1 0 1 0 1 would be another string it could recognize. 1 0 1 0 1 0 1 0 1 would be another string it could recognize. So repetitions of those are good. Now, when we write our machine, we identify a start state, okay, which is where the system begins. We have this notion of a recognized state, okay, so that's where you put, you know, an extra circle around the state to say I recognize the input. What's not specified is what should we do if we get a pattern that doesn't match this? Should we just, you know, go into the abyss and, you know, for the rest of eternity say I do not recognize that input pattern? Or should we go back to the start and try again, or what? So we're going to go with the abyss. Yeah, definitely. It's always easier to code that way. So we're going to start in an initial state, and if your input is exactly, you know, one of these recognized patterns, then we'll go to a recognized state. Otherwise, we'll just go to the abyss. So I'll have my start state, which I will just indicate, you know, with start. Sometimes it put an asterisk in the beginning for the start state and so on. And I'm not even going to have to number my states. I'm just going to draw pictures. Okay. So if we're in our start state and our input is a 1, then we're going to go to another state. And in this state, we're going to look for a 0. And if we find that, we'll go to another state where we're looking for a 1. But if, you know, we were looking for a 1 and we got a 0, or we got a 1 and we were looking for a 0 but we got a 1, or we got a 1 0 and we wanted a 1 but we got a 0, right? We'll go to the abyss. And once we're here, if we have a 0, we'll stay in this state. If we have a 1, we'll stay in this state. Now this is a pretty useless machine because you've only got one shot at getting the input right. But you know, we could have a reset button that you know brings you back to the start state. All right. So once we're in this state, what have we recognized? We recognized 1 0 1. All right. Now if I wanted to label these, I might choose to label them, you know, like this. Here's my start state. Here's my state S1, meaning I found a 1. Here's S10. Here's S101. Just to remind me what's going on. All right. What happens once I found a 101? I have to start looking for 01s. And I need at least one repetition of 01s. So I need to have a 0. And I need to have a 1. And again, any variance from that, and we don't recognize. Okay, now we found, you know, a 1 0 1 followed by one repetition of 0 1. This is a recognized state. Okay, this is a state we'll get to if our input is that. At this point, if we were to receive a 1, that's not part of our recognized pattern. But if we were to receive a 0, and then we were to receive a 1, that would take us back to a recognized state. But if we receive a 0 followed by another 0, then it doesn't match the pattern anymore. So yeah, it goes where all bad inputs go. All right, so that's just an example. The Isle of Misfit Bits, yeah. It's getting to be time for Christmas specials. The bits with the polka dots on it. All right, so yeah, so that's a peculiar looking state machine, right? But you know, that's one way to do language recognition. Now, if n was bigger than or equal to 0, right, we would probably go directly from here to this state here, which would say we'd seen, you know, 1 0 1, but that's a recognized state. And then if we get any number of 0 1s, each time we get a 0 1, we come back to a recognized state. And these aren't too bad to develop ourselves once you had some practice. They're not nearly as kind of quirky as Turing machines or Markov algorithms or some of these other more theoretical sounding state machines. All right, we're going to go through, Turing machine examples today and talk about Turing machines. So if you want to ask questions about these, we can, but we'll definitely go through some examples today also. What about question 5? Can you design a finite state machine that recognizes any string that contains the same number of zeros and ones? I asked it first, so I don't have to answer it. So what do you think? Can you make a machine that recognizes if you have exactly 2 ones and 2 zeros? Yeah, definitely. So if you want 2 ones and 2 zeros, here's our start state. So I'm going to call my states, S, A, B, which means we have A zeros and B ones. So this would be S 1 0. This would be S 0 1. If you have a 0, we're going to go to S 2 0. If you have a 1, we're going to go to S 1 1. If we have 0, we're going to go to S 1 1. If we have a 1, we're going to go to S 0 2, and so on, right? And if I get to state, 2 2, that's my recognized state. And I could do this for 3. I could make something that recognizes a string with 3 ones and 3 zeros, and 4 ones and 4 zeros, and a million ones and a million zeros. But could I do something that does that for any number of ones and zeros, tells me if I've seen the same number of each? So how might I do that? Or why might I not be able to do that? So are there limits on finite state machines? Let me ask you this. Could you write a C program to do this? Just have somebody type in ones and zeros one at a time, one per line, and have it tell you whenever you've seen the same number of ones and zeros. Yeah, I mean, we could do that in C, right? How do we do that? Make a loop, good. Make a loop with counters. What kind of variable will we use for those counters? It would have to be bigger than a bool. The output would be a bool, that's the true false, but what if we see 100 ones before we've seen any zeros at all? We need to remember that we actually saw 100 ones so that when we start seeing the zeros, you know, we can count those up, and when we get to 100 zeros, we could say, right? So yeah, we'd use something like an unsigned int. Is there a limit to how many ones we can count with an unsigned int? Yeah. So if we wanted to be able to detect the same number of ones and zeros up to, say, you know, 4 billion, we could definitely do that with a C program. But if we're going to allow somebody to enter, you know, trillions or quadrillions or skrillions of bits, we would need to do something fancier. And if there's no limit on the length of the string and the number of ones and zeros, we cannot write a C program that will solve this problem. We would need infinite memory, which, as someone just phrased in chat, an infinite number of states. Because basically each of these states tells us, you know, how many ones and zeros we've seen. And since there's no limit on the number of ones, even though it's always a finite number, there's no limit on the number of ones, there's no limit to the number of states that we need. So we would need an infinite state machine to do this. So this simple problem, tell me if we've got the same number of ones and zeros so far, can't be solved by an FSM. But in fact, it can't be solved with a C program either. But only in, you know, extreme cases. So if it was an infinite state machine, would it be possible? I don't know a lot about infinite state machines, but I'm guarantee there's a lot of literature out there on the subject, and I suspect it's probably possible. You need to define a language that you would use for describing an infinite state machine. But if you can do that, yeah, I mean, we could write, you know, something like this, and clearly it's possible, right? But I don't know much about ISMs. If our universe is a state machine, do you think it's finite or infinite?